The real number line is a fundamental mathematical object. You've probably seen it many times in the past, but there's a lot more here than meets the eye. The real number line is also called the continuum, and the symbol used to denote the real numbers is an R with a double stroke, often called blackboard bold. Before we explore some of the deeper properties of the real number line, let's remind ourselves of what a real number is. Real numbers include all integers. The integers, by the way, can be denoted by blackboard bold Z with a double stroke. That's from the German word for number, Zahlen. And examples of integers are 4, -1, 7, 0, -5, and you can go on and on forever. Real numbers also include the rational numbers. These are the same things as the fractions. And the rational numbers can be denoted by a Q with these double strokes. Q for quotient in this case. Examples of this would include 1/3, -2/5, 12/7, and so on. Positive and negative fractions. And real numbers also include irrational numbers. And there isn't a special symbol for irrational numbers. And these include other real numbers, decimals, such as the square root of 2, pi, -e, and so on. And so altogether, integers, rational numbers, and irrational numbers, these are the real numbers. And these are all the numbers that can be written as a decimal. So how do we go from the real numbers to the real number line? Now imagine if we first began by ordering these numbers in order from the smallest to the largest. The smallest of these numbers would be -5, and after that we would have -e, -1, -2/5, 0, then 1/3, the square root of 2, 12/7, pi, 4, and then 7. These are the sample real numbers that we're working with. Now what I'd like to do is draw a dot for each number. But what we want to do is we want to make sure the dots are spaced relative to the size of the numbers. So the numbers 1 and 2, for example, are closer than the numbers 5 and 30. And so we want to respect the size of the numbers when we draw these dots. We don't want to just draw them evenly spaced because these numbers aren't evenly spaced. So our smallest number is -5, so I'll draw that over here. And our largest number is 7, and so I'll draw that over here on the right. Somewhere around here would be the number 0. And so we're going to use these three numbers, -5, 0, and 7, as a way to guide us where the other number should go. So -e is -2.712828, so that's a little to the left of halfway between 0 and -5. So -e would be right around here. -1 would be somewhere around here. And -2/5 is -0.4, so that would be somewhere around here. Next, 4 is a little over halfway between 0 and 7, so that would go, let's say, here. Pi is 3.14, so it's a little beyond where you would expect 3 to go. So let's put pi there. And then we have 1/3, which would be quite close to 0. We'll draw a dot there. The square root of 2 is 1.414, etc. It goes on forever. And we will put a dot here for the square root of 2. And then 12/7 is 1 and 5/7, and that would go right around here. So these are the 11 sample real numbers that we chose. Integers, rational numbers, and irrational numbers. And we went through and we drew a dot and spaced it out as best as we could, not worrying about being overly precise, drawing one dot to represent each number. And we arranged them from the smallest number on the left to the largest number on the right. Now, we could go through and keep picking more and more integers, more and more rational numbers, more and more irrational numbers. And as we do that, the dots will rapidly fill up the spaces. Like we could pick 10,000 numbers between -5 and 7. And by the time you were done drawing them all, what would happen is all these points would blend together into a line. Now, the reason for that is if you were to get really close with a ruler, you could measure the width of the dots that I drew next to each number. And so when we run out of space, you could think, well, why don't we just redraw it again? Let's draw it over again, except use smaller dots, teeny tiny dots next to each of the 11 numbers that we picked. And then you could go through and say, let's now pick a billion numbers between -5 and 7. You would draw in a billion teeny tiny dots. Once again, you would get this solid line. And so you might even want to go smaller. What if you went so small as to where every dot was like a hydrogen atom, the smallest atom that there is? And so between -5 and 7, you arranged a massive number of numbers, and you put one atom next to each number, and they would still get too crowded eventually. You'd run out of room to put atoms to represent other numbers. And that's because we're so used to drawing a dot to represent a number that it's easy to forget sight of the fact that a point, a mathematical point, has no size. It's zero-dimensional. It does not have a width, a height, or a depth. We draw it as a dot so we can see it and we can point to it and talk about it, but in reality, points have no size. And so there's an infinite number of real numbers, and we could draw an infinite number of points, one point for each number, one number for each point, and arrange them from smallest to largest. That is the idea that we're trying to capture with the real number line. By the way, the arrowheads at both ends of the real number line are there to remind you that this line goes on forever in both directions. So now we're going to entertain some deep thoughts about the real number line. So you might need to just be very calm, very still, meditate for a brief moment while I draw a real number line. Here we go. We have a nice line here that represents the continuum, the real numbers, which we can denote by this R with a double stroke. Suppose we draw a dot here to represent the number 0.351. Here's the question I'd like you to think about. What number comes after 0.351? You might want to just hit pause, close your eyes, think about that for a moment, and when you're ready, resume. It turns out there is not a number that is directly after this, and here's why. Suppose you have a number A, and we'll draw a dot to represent that, and we have another number B, represents that. Then if you look at the average of A and B, you get a number that's halfway between them. So no matter how close they are to one another, there's another number that lies between them. So if there was a number that came after 0.351, you could just average that number and this one to come up with a new number that's actually in between them. And that reasoning lets you see that there is not a number that comes right after it. And that's another interesting feature of real numbers, which when you stop to think about it, makes you realize that no matter what two numbers you pick, let's say we picked a number 0.352, the number of numbers between these two numbers is also infinite. And you can see that because if you were to take the average of these two numbers, you would get a number halfway between them, which I will draw a little line right there because it's starting to get a little bit crowded. Well, you could then take the average of the first and second points, and then the average of the second and third points, and you would get additional points halfway between those. And you could continue this process over and over again. And in that way, you could see that there is an infinite number of numbers between any two numbers on the real number line, no matter how close they are to one another. So now I'd like to think about the question, why? Why create the real number line? We have this idea of real numbers, positive, negative, zero, all different types of decimals. Why bother with drawing a line and keep referring back to that when you're learning mathematics? Well, there's several reasons. One is visualization. As you work with equations and inequalities, it will be good to be able to draw a real number line so that you can take the solutions and kind of visualize the answers you get to the various math problems. Another reason the real number line is important is it's helpful to imagine and talk about some more advanced math topics. The further you go in mathematics, you'll start to encounter some more advanced ideas and concepts, things like continuity, convergence, uniform convergence, things like that. And being able to use the real number line as a visual aid is very helpful. And the third, which is related to the first, is the Cartesian plane. Let's clear the screen again, and let's draw a Cartesian plane so you'll better see what I'm talking about. The Cartesian plane has an x-axis, so we will label with x, and then orthogonal to this is a y-axis, which I will also label. If you look at it straight on and then rotate your head 90 degrees and look at it sideways, you'll notice that the x-axis is a real number line and the y-axis is a real number line. And this is useful when you're visualizing equations that have two variables in them, an x and a y. Solutions to equations and inequalities will correspond to points in the plane, just as solutions to equations and inequalities with one variable correspond to points on the real number line. And in fact, you don't even have to stop at 2 dimensions. In this way, you're now using 3 real number lines, all orthogonal to one another. They make a 90-degree angle with each other. This is a way for you to visualize equations and inequalities that have 3 variables, x, y, and z. So while the visualization on 1 dimensions is somewhat helpful, and the further you go in math, you'll continue to revisit the real number line to visualize certain concepts. When it comes to just visualizing equations and inequalities and systems of equations and systems of inequalities, it's really key to be able to have a picture in mind as to what's going on